Other reactions that we can do include a hydrohalogenation. So we're going to add HX to the alkyne, just as we did with the alkenes. The hydrogen went to the carbon with more hydrogens, and the halogen went to the carbon that was more substituted, which was the Markovnikov product. We have the same thing with the halogen and the alkyne, except we leave a double bond behind, but the halogen adds to the more substituted carbon. This occurs in about 60 to 80% yield. If you add an excess of the halogen, we'll add 2 halogens to the same substituted carbon. This also has the Markovnikov selectivity. Just like with alkenes, we can change the selectivity by using a peroxide. So this alkyne with HBr ROOR will give us the double bond with the halogen, give us the bromine at the less substituted position. We'll also get the other isomer there. So we'll get a mixture of E and Z isomers. And that happens in 82% yield. Like alkenes, alkynes can also undergo acid-catalyzed Markovnikov hydration. This process is usually catalyzed by mercury sulfate to compensate for the slow reaction. So it's going to go through a vinylic carbocation, and that is very slow, so we need that mercury sulfate to speed up the reaction. So what we'll see happen is, just like in the alkenes, the water gets added. We have the double bond here. The OH goes to the Markovnikov product, or the more substituted. This here is called an enol. So we have the alkene plus the alcohol, so this is an enol, but this is not isolated. What happens instead is we get a little bit of a shuffle of protons, and we get a ketone instead. So when we have the enol, the double bond can do a proton transfer. So these electrons from here will grab a hydrogen from the acid that is in solution, the H2SO4, and then we give water off there. When that double bond picked up the hydrogen adds to the carbon with more hydrogens. This becomes a carbocation. And this is resonance stabilized. You can imagine drawing these electrons to here. And we form this double bond here, and the positive now is on the oxygen. So this is resonance stabilized. We can then do another proton transfer with the water. That will take the hydrogen, and the electrons will go on back onto the oxygen. And that's where we get the ketone from. So this enol ketone tautomerization, as it's called, cannot be prevented, so we can't stop it at the enol. And these are constitutional isomers that rapidly interconvert between each other. So the enol and ketone, these are tautomers of each other. And this process here is tautomerization. We can also hydrate the alkynes using hydroboration-oxidation. Just as before, we're using the borane in order to change the regioselectivity. We'll have the R, and we get the double bond here. Hydrogen adds here, and then we get an addition of OH on the end. So this goes to the least substituted carbon. This is an enol. We do another tautomerization. And we get the aldehyde. So the mechanism here is almost the same. The hydroxyl group in the NaOH can grab the hydrogen, which brings the electrons onto the oxygen. We have the O minus. That is in resonance with this. If we take these electrons down to here, and it goes on to this carbon, so this is an enolate. So the 8 tells us there's a minus charge there. And then we have water floating around, and we do another proton transfer. So with the hydroboration and an alkyne, we get an aldehyde. And that is the anti-Markovnikov product. After the BH2 and H groups have been added across the double bond, in some case we can get an undesired product. So this is if we use BH3 with the alkyne. We'll get an aldehyde and this BH group. And it can react with another BH2 or BH3, and we get an undesired product. So in order to avoid that, we often will use a different bulky borane. So you can use diisolamyl borane, which looks like this, or you can use 9-BBN. You don't need to know the structure of either of these. You can just write 9-BBN or diisolamyl borane. For example, this reaction here, we have 1 diisolamyl borane followed by H2O2 sodium hydroxide. We have a 4-carbon chain. It goes through the enol, and that will tautomerize to the aldehyde. So if we were now working backwards, you want to draw the alkyne that could be used in order to make this molecule. What we're looking at here is a ketone. And we can think about reactions where you have an alkyne that would give you a ketone. If we use this alkyne and reacted it with H2SO4, H2O, HgSO4, that would get us the ketone. You could try to do an alkyne if you wanted to choose a different spot to put the alkyne. Here, this would not work because we have 5 bonds to carbon. We can do Markovnikov hydration. So just a quick review, the Markovnikov hydration will lead to a ketone. And the anti-Markovnikov will lead to an aldehyde. So in this reaction with the sulfuric acid, water, and mercury sulfate, we'll get a ketone. This R2BH, this can be the 9-BBN or the diisolamyl borane. We will get an aldehyde. We can halogenate alkynes as well. If we have an excess of halogen, we'll add 4 halogens across the triple bond. That occurs in 60 to 70% yield. If you add only 1 equivalent, we'll get the Z and the E. This is the major product. That is minor. So this halogenation undergoes anti-addition. Just like with alkenes, we can do ozonolysis. However, when we do ozonolysis with alkynes, there's often a water workup. We'll still see the cleavage of the triple bond, but instead of leaving a ketone and aldehyde, we're going to get two carboxylic acids. So we'll take that apart. You have the ketone part of it, and then we also add this OH group on there. So we get the carboxylic acid. So this water is an oxidative workup. And that's where the extra OHs come from. So if we cleave this here, this becomes our carboxylic acid. If you have a terminal alkyne, that will become CO2. So if we do the reaction here with this dicyclohexyl alkyne, we cleave. We can alkylate terminal alkynes, which means that we can use this to add carbon bonds. So if you recall from the beginning of this chapter, alkynes have acidic protons, which means that we can deprotonate it. That makes it a good nucleophile. So if I had this base here, I'm going to go fishing for this hydrogen, which will add the electrons to the carbon. So we have this lone pair and a negative charge. This is an alkynide ion, which is also a really good nucleophile. So once you have this nucleophile, you can add it to an electrophile, which also contains a leaving group. And we can do an SN2 reaction. We have this nucleophilic attack and the loss of a leaving group. And then now we've added a carbon and a new R group here. So this is a new carbon bond that formed. These alkynides react best with primary alkyl halides. The secondary and tertiary can undergo elimination. So if we have this NaNH2, which is the base that we used up here, that will go fishing for this hydrogen. The electrons go on to there. And if you notice, the alkyne stays intact in all of these reactions. We don't lose the alkyne, it still is there. So that was step one. We form this alkynide, then we have ethyl iodide. We can do the nucleophilic attack. And then we've added two carbons and extended the chain. Acetylene can be used to perform a double alkylation. If you have acetylene, which is the 2-carbon triple bond, you can do a reaction with the 2 carbons. We add 1 ethyl group. You have your acetylene with the 1 ethyl group. And then we can add 1 to the other side using the same type of reactions. What we cannot do is add this alkyne here with 2 equivalents of sodium amide. We cannot do that reaction. Order of addition is important. If you noticed here, we did 1 step first, got the product, did the second step, got the product. If you wanted to add ethyl groups twice here, we would need to do the acetylene, NaNH2 with ETI, and then repeat that again.